In this example, we're asked to show which of the series converge absolutely. For absolute convergence, we need only check if the sum of the absolute values of the series converges. Starting with the series on the left here, we see that the sum of the absolute value of minus 1 to the n over n cubed plus 2n is just the sum of 1 over n cubed plus 2n, because the absolute value of minus 1 to the n is just 1. To demonstrate convergence with the comparison test, we must show that the terms of the series are less than or equal to the terms of a series that converge, and to show divergence, we must show that the terms are greater than or equal to the terms of a series that diverge. Of course, we need to check that the terms of the series are positive before we apply the comparison test, but that's true here because we're looking at the sum of the absolute values of the terms of the original series. Now, n cubed plus 2n is bigger than or equal to n cubed for n bigger than or equal to 1, so therefore 1 over n cubed plus 2n is less than or equal to 1 over n cubed for n greater than or equal to 1. We know that the sum from 1 to infinity of 1 over n cubed converges because this is a p series with p equal to 3, which is greater than 1. Now we can conclude that the sum of 1 over n cubed plus 2n converges by the comparison test. From our comparison above with the series, the sum of 1 over n cubed, which we know converges. And therefore we can conclude that the original series, the sum of minus 1 to the n over n cubed plus 2n, is absolutely convergent. Now let's see if we can figure out if the second series on our list is absolutely convergent. Obviously, the sum of the absolute values of the terms of the series is a series with positive terms, so we can apply the comparison test to see if it converges. Since the absolute value of cosine n is always less than or equal to 1, we have the absolute value of cosine n over 2 times e to the n plus 1 is going to be less than or equal to 1 over 2 times e to the n plus 1, and since 2 times e to the n plus 1 is greater than or equal to e to the n, this in turn is less than or equal to 1 over e to the n. Now the sum from 1 to infinity of 1 over e to the n is a geometric series with the absolute value of r equals 1 over e, which is less than 1, so therefore it converges. Thus, the sum from 1 to infinity of the absolute value of cosine n over 2 times e to the n plus 1 converges by comparison with the sum from 1 to infinity of 1 over e to the n, and therefore our original series, the sum from 1 to infinity of cosine n over 2 times e to the n plus 1, converges absolutely. Now let's look at the third series on our list, which should actually start from n equals 2 and run to infinity, because if n is 1, n minus 1 is 0. The sum from 2 to infinity of the absolute values of minus 1 to the n over n minus 1 is equal to the sum from 2 to infinity of 1 over n minus 1. Since n minus 1 is less than n for n bigger than or equal to 2, we have 1 over n minus 1 is bigger than 1 over n for n greater than or equal to 2. The sum from 2 to infinity of 1 over n diverges because it is a p series with p equals 1, or the harmonic series, whichever way you like to think about it. Therefore, by the comparison test, the sum of 1 over n minus 1 diverges because its terms are larger than that of a series which diverges. And thus we can conclude that the sum from 2 to infinity of minus 1 to the n over n minus 1 does not converge absolutely. It does converge, but the convergence is conditional, and you can see that it converges by the alternating series test. And now let's test the last series on our list for absolute convergence. Again, because the absolute values of the terms are positive, we can apply the comparison test if we can find an appropriate series to which we can compare the sum of the absolute values. Now, as before, we see the absolute value of cosine n is less than or equal to 1, so the absolute value of cosine n over n squared is less than or equal to 1 over n squared. And we know that the sum from 1 to infinity of 1 over n squared converges because it's a p-series with p equals 2. Therefore, by the comparison test, the sum from 1 to infinity of the absolute value of cosine n over n squared converges. And thus we can conclude that the sum of cosine n over n squared converges absolutely.